Welcome back to the Explainer. Today we're going to break down one of those classic mechanics problems from the Irodov collection. You know, the ones that really make you think.
So we're jumping right into a really fun puzzle. It's one of those questions that seems a little backwards at first. Can a spring that's pushing down actually make something jump up? This is a great one from Irodov's legendary book of problems.
Okay, so picture this. You've got two identical cubes. In between them is a spring that's all squished down, and a tiny little thread is holding the whole thing together on the ground. The big question is, what happens when we burn that thread? Does the whole thing just pop, or can it actually lift off the ground?
All right, let's get into it. You know the drill with any physics problem, right? The very first step is to figure out what tools we have in our toolbox. Which laws of physics are actually going to help us unpack this thing?
Okay, first things first, and this is super important. We have to define our system. What are we actually looking at? For us, the system is the two cubes and the spring. We're going to treat them all as one big interconnected thing that's dealing with an outside force, which in this case is just good old gravity.
So whenever you see a problem with springs, things moving, and heights changing, two big ideas should pop into your head. The first is the law of conservation of energy. It's perfect for connecting the energy stored in that spring to how the cubes move. And the second is Newton's second law, which is going to be key for analyzing the exact forces at play when liftoff happens.
All right, let's dive into part A of the problem. What it's really asking for is a kind of tipping point. What's the absolute minimum amount we need to compress that spring so that the bottom cube will eventually, bounce off the ground?
Now, before we even touch a pencil to paper, let's just stop and think. What does it physically mean for something to bounce up or lift off? What's happening with the forces at that exact moment?
So liftoff happens at the exact instant the ground isn't pushing on the cube anymore. You know that upward push from a surface? We call that the normal force. So the condition for liftoff is simply when that normal force goes to zero. If at that same instant, there's some other upward force that's bigger than the cube's weight, whoosh, it's going to accelerate upwards.
Okay, now this right here is the absolute key to the whole problem. That's where a lot of people get tripped up. The force that actually lifts that bottom cube, it's not from the spring pushing up initially. Think about it. The top cube shoots up first, right? And when it does that, it stretches the spring. It's at the very peak of its motion, when the spring is stretched to its maximum, that it pulls up on the bottom cube with the biggest force. That's the moment we got to focus on.
So here's our plan of attack, all laid out. We're going to use energy conservation. Step 1, figure out the initial energy. That's easy. It's all just potential energy stored in that squished spring. Step 2, figure out the energy at that critical liftoff moment we just talked about. At that point, the initial energy has transformed into two new things: gravitational potential energy for the top cube, because it's higher up, and potential energy in the now stretched spring. All we have to do is set the before energy equal to the after energy, and we can solve for what we're looking for. And when you work through the math, which is just a bit of algebra, you get this really clean, elegant result. For that bottom cube to actually bounce, the initial compression, delta L, has to be greater than 3 mg/k. It's that simple. Okay, let's move on to the second part of the problem. This time they give us a number. They say, what if the initial compression is this specific value? And they want to know how high the system's center of gravity goes. And remember, the center of gravity is just, it's kind of like the average location of all the mass in the system. So the problem tells us the compression is 7 mg/kappa. Now remember what we just found? The liftoff threshold was 3 mg/kappa. Well, 7 is way bigger than 3, so we know for sure this thing is going to jump. No doubt about it. Now we just have to figure out how high.
So, first step is to figure out how much energy we're starting with. We just use our trusty formula for spring potential energy. 1/2 kappa times the compression squared. We plug in that 7 mg/kappa value they gave us, crunch the numbers, and we get the total initial energy of the system.
Okay, here comes the second really big aha moment of this problem. As soon as that bottom cube is airborne, what's the only external force acting on our whole system? It's just gravity. And that's a huge deal because it means the system's total energy is conserved. All that energy that was initially stored in the spring has to go somewhere, right? Well, it all gets converted into the work needed to lift the entire system, both cubes, against gravity.
Yeah, this table really sums it up perfectly. The energy starts in the compressed spring. And where does it all end up? It ends up being used to do work, specifically lifting the total mass of the system, that's 2 mem, remember, up to some height, h.
So, the final step is pretty straightforward. We take that initial energy we calculated a minute ago, and we set it equal to the work done against gravity, which is just the total weight, 2mg, times the height, h. We solve that simple equation for h, and boom, there's our answer. The center of gravity rises by 8 mg over kappa.
Okay, so we got the answers. That's great. But let's zoom out for a second. What are the big strategies we used here? What are the key takeaways you can use for other problems?
I think there are a few really crucial things to remember. Number one, always define your system before you start. It saves so much confusion. Number two, get good at turning words like bouncing up into actual physics equations, like setting the normal force to 0. And finally, never forget how powerful conservation of energy is. It's often the simplest way to connect what's happening at the beginning of a problem to what's happening at the end. And to wrap up, here's a little something to chew on. We solved this whole thing using energy, right? But what about momentum? Think about a rocket launch. It shoots hot gas down to go up. Our system kind of pushed one cube up, which then pulled the other one up with it. How does the law of conservation of momentum play a role in both of these situations? How are they similar, and how are they different? It's a great thought experiment.